You can use a number, a string, or a tuple as a dictionary key, but never a list. Python simply won't allow a mutable object as a key. The reason isn't arbitrary. It comes from how a dictionary physically stores its data. Understand that, and you'll also see how to nest dictionaries inside dictionaries. Let's start with the mechanism, hashing. Every dictionary operation starts with the key you want to store. Python runs a hash function on that key. If the key is a number, the hash function might hand back that same number or a different one. If the key is a string, a run of characters, the hash function converts those characters into a number. Either way, the rule is the same. A hash function takes your key and produces a single integer. Think of that integer as a memory location, a slot where the value for this key will live. Python stores the value at that slot. Later, when you look the key up, Python runs the very same hash function on the very same key, gets the very same integer back, and then jumps straight to that slot to read the value. The function never changes. So a given key always leads to the same location. That is what makes a dictionary lookup fast and reliable. Now here is the catch. Suppose the key is a mutable object, something that can change after you store it. When you hash a change object, the number that comes out may be different because you altered the very thing you fed into the function. There is no reason it would return the same slot. To see exactly how that breaks a lookup, let's walk through a concrete example. Imagine our memory has just 16 slots numbered 0 through 15. Each slot holds one student's grade and the hash function takes the student's name. Our made-up function gives each letter its place in the alphabet. The letter A is worth 1, B 2, C 3, and so on. It sums those numbers for every letter in the name, then takes the sum modulo 16, the remainder after dividing by 16, which always lands between 0 and 15, a legal slot. Take Anna, 1 plus 14 plus 1 is 16, and the 16 modulo 16 is 0. Anna's grade goes in slot 0. The same recipe places everyone. Eric, 5 plus 18 plus 9 plus 3 is 35, and 35 modulo 16 is 3. So Eric lands in slot 3. John, 10 plus 15 plus 8 plus 14 is 47, and 47 modulo 16 is 15. So John lands in slot 15. Now retrieval. To find Anna's grade, we hash her name again. Anna is a string, and the strings can be changed, so the function returns 0 once more. We jump to slot 0 and read her grade straight back. Because all three names are immutable, all three grades can always be found. Now the failure. Suppose we store a student's name as a list, so the name can change. Kate hashes to 11 plus 1 plus 20 plus 5, which is 37, and the 37 modulo 16 is 5. Her grade, a B, goes in slot 5. Then Kate changes the spelling of her name from Kate with a K to Kate with a C. It's the same object and she still earned that B, but hash the new name. 3 plus 1 plus 20 plus 5 is 29, and the 29 modulo 16 is 13. Python now looks in slot 13 and she isn't there. Her grade still sits in slot 5, unreachable. The student has vanished. That is precisely why a mutable object can't be a dictionary key. Change the key, and the hash may point somewhere else entirely. Back to storing a whole class's grades. The old approach, a master list of lists, forced us into nested loops and nested conditionals. A dictionary of dictionaries is far cleaner. Here it is. The outer dictionary, my D, has 3 entries, 1 per student, the key Anna, the key Fredo, and the key Eric. The value for each name is itself a dictionary, allowed because a dictionary value can be any object, including another dictionary. Each inner dictionary has 2 entries, 1 keyed MQ for the micro quizzes, 1 keyed PS for the problem sets, and each value is a list of scores. Notice the inner keys aren't in the same order. Anna's starts with MQ, Fredo's with PS. That doesn't matter at all because a dictionary has no order. Suppose we want one student's first quiz score. The old code to nested for loops and the nested ifs collapses to a single expression. My D indexed by Eric, then by MQ, then at position 0. Read it left to right. First, my D indexed by Eric looks up the key Eric and returns Eric's entire inner dictionary. That result is indexed again by MQ, which returns the value stored under MQ, the list containing 3. Finally, we index that list at position 0, grabbing the 3 itself. So Eric's first quiz score was a 3. Not great. Here's an exercise to reason about rather than type. This function, getAverage, computes the average of one category of work across the entire class. Give it the class dictionary and the string MQ, and it should average every micro quiz. Give it PS, and it averages every problem set. It starts with an empty list called all data, then loops over every student key. The one missing line is the body of that loop, and the question is which version fills it correctly. When we call getAverage on my D with MQ, we expect it to average Anna's 10, Fredo's 8, and Eric's 3. 21 divided by 3, which is 7.0. There are 4 candidate lines, all lettered. Option A, all data equals all data plus data, indexed by start, then by what. Option B, all data dot append of data, indexed by start, then by what. Option C, all data equals all data plus data, indexed by start, indexed by what. Option D, all data dot append of that same start, indexed by what. The whole trick turns on what each version actually produces. We need all data to end up as one flat list of numbers. For the problem sets 10, 10, 7, 8, 0, because only a flat list of numbers can be summed. Start with the tempting one. Option B, append. Ask what data indexed by start then by what really is. Indexing my D by a student gives that student's inner dictionary. Indexing that by MQ gives a list, not a number. Append doesn't spill a list's elements in, it drops the whole list in as a single element. So all data becomes a list of 3 lists, the list containing 10, the list containing 8, and the list containing 3. Then sum tries to add those lists onto a running integer total, and Python crashes with a type error. Unsupported operand types for plus, an integer, and a list. Append is wrong. Options C and D fail for a different reason. Look at where the inner brackets sit. Both write data indexed by, and inside that, start indexed by what. The inner part indexes stud, a student's name, with the string what. But stud is a string, and a string can only be indexed by an integer, never by another string. So the moment Python evaluates it, both crash with a type error. String indices must be integers, not a string. Neither C nor D even gets as far as building a list. That leaves option A, concatenation, and is the answer. The plus operator joins 2 lists end to end, flattening as it goes. Starting from the empty list, all data grows, plus Anna's list gives 10, plus Fredo's gives 10, 8, plus Eric's gives 10, 8, 3s, one flat list of numbers. Sum is 21 divided by 3 students gives 7.0, exactly what we expected. The insight to carry away, indexing an inner dictionary by MQ or PS, returns the value stored there, and that value is a list, not a number. For Anna, MQ is the list containing 10. PS is the list 10, 10. Because you're gathering lists, you concatenate them, you don't append. 3 ideas tie this together. First, a dictionary stores each value at a slot chosen by hashing its key, then rehashes the same key to find it again, so if the key could change, its value will be lost, which is why keys must be immutable. Second, because a value can be any object, a class record becomes a dictionary of dictionaries, and the retrievals that once needed nested loops collapses to a single chained lookup. Third, indexing an inner dictionary returns a list, not a number, so you gather scores by concatenation, not by append. Values can be anything. Keys must hold still. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.